Hello. My voice is
I think you guys might need intro music. It's a bit difficult to go from we were talking normally to hey guys,
I
welcome
know,
to
I
our
know.
podcast. Like,
Hello, and welcome to another episode of Physics Chat, the show where we get to know a modern day physicist and their field of research. I'm here with my co hosts, Sergi and Joe. How are you guys?
Very good, thank you. How are you?
Good, thanks, Dan.
I'm great. And I'm also here with our very special guest for the episode, a cosmologist at the University of Cambridge who is researching supernovae, Suhail Dhawan. How are you?
fine, thanks. How's it going?
Yeah, going good.
So it's great to have you on the show, Suhail. But first, let's get to know you a little bit. Have you done anything interesting in this week?
Yeah, so I was volunteering at a dog shelter this last weekend. I do that fairly regularly. Yeah, it's something I'm quite passionate about outside of science. I did one in Washington, D.C. called Humane Rescue Alliance. Those guys are amazing if anyone's on the East Coast. And there's a great shelter near Cambridge called Wood Green Charity. And as funny as this sounds, I'm trying to organize a chocolate tasting event to raise some funds for them.
Well, that sounds amazing. So we will be sure to include a link in the description to that charity. But let's get into some physics. Could you explain your research in a sentence?
Right. So I use exploding stars to measure how fast the universe is expanding today.
Okay, there's a lot to unpack there. It might be obvious to you, but why do stars explode and how do they explode?
There's a particular class of explosions, and these come from stars that are as massive as our sun, but they're actually the size of the Earth. So that makes them very, very dense, but they're also very stable. Now, stable stars, we wouldn't expect them to explode. But what happens is, in nature, most stars actually exist in binaries, and that is what causes the instability that we need for the explosion. There is a companion star to this dead compact star that we have, which is known as a white dwarf. And the companion starts dumping a lot of material on the white dwarf. As a result, it causes a level of instability, which causes it to explode at a characteristic scale and mass. So this is one type of star which people may have heard of. It's called a supernova of type 1a. And that is what I'm particularly excited about for measuring the expansion.
Interesting to learn about different types. What is it about this type that makes it so useful or special to you?
Historically, in astronomy, distance measurements have always been very hard. One of the central ideas in distance measurements has been to use objects that have a characteristic brightness, because by seeing their apparent brightness and comparing it to this characteristic brightness, you can then infer a distance. That distance, along with other information, gives us the expansion rate of the universe. So that's particularly why these classes of stars are useful. They are typically known in astronomy parlance as standard or standardizable candles.
So this expansion of the universe is something a bit difficult to understand. How did we come to this conclusion?
I'm going to do a subtle plug for a show actually that I saw recently, which was called The Dark Universe at the Smithsonian in Washington, D.C. And I was very happy to see that they gave a great historical background for where we got to know this from. So there was an astronomer, Vesto Slipher, who did a lot of measurements of the velocity at which other galaxies are receding from us. So this is typically what is known as a redshift. And there was another astronomer at Radcliffe Observatory or Harvard College Observatory, like in the Harvard area, Henrietta Leavitt, who's a stalwart in 20th century astronomy and cosmology as a result. And looking at the characteristic pulsation of a class of stars called Cepheids, she deduced that that was correlated with the luminosity. And as I previously mentioned, the luminosity, when being characteristic, can give you an accurate distance. So Cepheids became very good distance indicators as a result of the Leavitt 1912 paper. And Edwin Hubble at Mount Wilson and the 100-inch telescope used some of the redshifts from Vesto Slipher cipher and the method from Henrietta Leavitt, and found that those objects that are farther away are also receding faster, and that led to the inference the universe is expanding. And that was the first evidence. There's some debate on like sort of other bits of evidence on how we came to this conclusion, but ever since then the data has gotten better, and we've reached this conclusion through multiple different ways and are able to measure this quite precisely.
You mentioned redshift, and I think that's something that the non-physicist or non-cosmologist especially will not be very familiar with. So why do we want to measure these distances in redshift rather than in meters or kilometers? Or
so a distance alone is not enough to infer that the universe is expanding. What we need is to see the light from the faraway galaxy as it is split into its constituent colors. When we compare where we expect a particular component of the light, which may be coming from a certain element in that galaxy, is in our laboratory compared to what we see as the wavelength of that light, that shift along with the distance gives us the conclusion that the universe is expanding. And that is what we call a redshift.
We now have lots of ways we can measure the expansion rate of the universe. Why, as a community, are we so invested in measuring this quantity right now?
100 years ago, we were essentially just looking for, is the universe expanding or not? And there were a lot of things that were very imprecise when it came to astronomy and like cosmology. Now, in decades since, we have improved a lot when it comes to both instrumentation as well as our understanding of these physical objects. It's led us to have a standard model in cosmology, and this standard model predicts, based on the first light of the universe, an expansion rate of the universe. Also, we can directly measure this much, much more precisely than what Hubble could. And because of that, we now have a prediction and a direct measurement. And these two, which are both independently very precise, do not agree with each other. This could have one of three implications. One, we don't understand something about the measurement in the early universe. Two, we don't understand something about the measurement in the late universe. Or the third implication, which is what really is making everyone very excited, is we don't understand something about the model that we use in order to get that inference. And if that is the case, we are on the cusp of a very interesting new discovery. And that's why people are trying to figure out which of these three it actually is.
Always interesting to hear about in science when there's a disagreement, which sounds quite bad, but it's an area where a lot of new physics can go into. So what is it that you were trying to do with these supernova to resolve this tension?
That's a great question. We're trying to currently utilize different populations of stars to see whether it's something about the stars that we use for distance measurements that we don't understand, or whether it's actually pointing towards something fundamental we don't understand about the universe. The thing is, one of the ways these supernovae are used in order to measure the expansion rate is by getting distances to the galaxies that they explode in using these Cepheid variables, which are preferentially young stars. What I'm interested in is also using old stars in order to get distance measurements to see whether or not those two values agree. That's something that we can now do with the James Webb Space Telescope, because these old stars are bright in the infrared, where JWST is most sensitive. Another thing that I'm quite excited about is using supernovae in a completely different way, which is through the phenomenon of strong lensing, which is similar to how optical lensing happens, but lensing by a massive gravitational object. And this is something that's very independent of any sort of distance scale measurement to the host galaxy. And instead of actually using them as standard candles, we end up using them as standard clocks, because the difference in the arrival time of the different images is characteristic of the expansion of the universe. So that's why they are standard clocks in that domain and candles in this domain, which makes it very independent.
That's excellent. I'm thrilled to say that we're going to have another episode following up from this point with another guest talking about strongly lensed supernovae. So that's going to be great. Stick around. But this seems as good a time as any to ask our traditional physics chat random question of the episode. It's not entirely random. We know you love dogs. You mentioned that you volunteer at charity. Which type of dog would you say describes your personality?
I'm a big fan of Indian street dogs because they are extremely friendly. They will honestly have extreme amounts of loyalty as well. And yeah, I feel a certain sense of rooting for the underdog because they get neglected quite a lot. Yeah, I'm not sure if that's like the best answer, but that is like my one way of doing a subtle plug for Adopt Don't Shop.
Of course. What about you, Sergi?
Knew you were gonna ask it. So yeah, I don't know. So that's why I took a dog personality test, and apparently I'm a beagle.
Beagle.
Don't know why, but yeah, that's what the internet says.
I was thinking we've got one of the members of our department has a black Labrador called Austin, who is fantastic and spends his time lying in the sun and eating everything he can. So if I could be like Austin, that'd be pretty good. How about you, Dan?
That's great. Shout out to Austin. Yeah, I mean, you get along with dogs that match your personality, right? And I got along very well with my dog. He was a border collie. I loved him. He was fantastic. So I guess I'm border collie because they're great.
Does it look like you or?
Not at all. He was a reddish variant of a border collie. So
okay.
red hair,
I was thinking about this scene in the Dalmatians. Don't know if you remember, where there's the owners and the dogs, and they're like just walking in the park, and they all like look the same.
Yeah, not quite, but yeah.
So Suhail, maybe to get to know you a bit more, what or who inspired you to become a physicist?
So I was quite inspired by a documentary I saw on Jocelyn Bell when I was in high school, and just meeting her when I did like an RDU program at Oxford was something that I went like, oh my God, I can't believe that, like, you know, we're even in the same postcode. And yeah, ever since I've just been like, yeah, it's not just that like you have people who've made amazing discoveries, you also meet people who are just generally like super helpful and kind and nice, and it's like, this seems like a thing I would like to do for the rest of my life if I get the chance.
I guess what we'd ask you as well is if there's any kind of advice you could give to your younger self from where you are now, what do you think you would tell them?
Yeah, I think I'm very excited about like to whatever degree being able to help and mentor younger people. And if I were to tell them or my younger self something, it would be that the people in the establishment or like whether you're applying for PhDs or early career research jobs, they need you as much as you think you need them. That is a attitude shift that I would have liked in myself, and I hope that helps people.
I think that's fantastic advice. Thank you for sharing it. And thanks so much for being on our show. We hope the audience has found this episode as interesting as we have. Please do leave a comment about how much you love dogs. And a reminder that there are lots of dog shelters out there, just like the ones Suhail talked about, which do great work. So maybe consider donating if you're able to. And because we're not done talking about supernovae just yet, we'll see you in the next episode. But for now, from all of us, goodbye.
Bye.
Bye.